Today we are going to discuss about decoding of turbo codes. So, to do that we will first review our BCJR algorithm in the log domain. We have talked about BCJR algorithm in the probability domain. We will very quickly review the metrics that are updated in BCJR algorithm and how they are implemented in the log domain, and then we will talk about turbo decoding. We will take an example of a rate 1/3 code. So, this is the block diagram of a turbo decoder. As you can see, the main blocks here are, so recall a turbo code consists of parallel concatenation of two recursive convolutional encoder. So, here we have two decoders, it is an iterative decoding process. We have two decoders corresponding to the two encoders. So, this is one decoder, this is second decoder. Now, note I have written soft input, soft output decoder. Now, what do I mean by soft input, soft output decoder? So, the input that this decoder receives are the real channel received values. These are not quantized to zeros or ones, as opposed to getting zeros and ones in case of a hard quantized decoder. Here we are getting the noisy receive sequence from the directly from the channel, and that is what we are calling as soft input bits. The output is also soft. What do we mean by soft output? Now, the decoder will output not only the decision about whether the bit it thinks is 1 or 0, but it will also give us some information about with what probability it thinks the bit is 0 or 1. So, not only we are getting information about the decision of whether the bit is 0 or 1, but we are also getting some information about how likely the bit is going to be 0 or 1. That is why the input here is also soft and the output is also soft, as opposed to a hard decoder where the output would have been just zeros and ones. So, if you look at this decoder structure, now recall our encoder diagram for a turbo code. So, what we had was, we had one encoder, right, and this was an information sequence. Now, this information sequence was permuted using an interleaver. I am denoting the interleaver by pi, and then this interleaved signal was sent to another encoder, and the three outputs were, first was this information bits, second was this parity bit coming out of the first encoder, and the third is the parity bit coming out of the second encoder. So, these were the three outputs of a turbo decoder. Now, after these bits pass through the channel, what you are going to receive is noisy version of the information sequence, noisy version of this parity bit, and noisy version of this second parity bit. Now, as I said, we are using two decoders, one decoder to decode this convolutional encoder, the second decoder to decode this convolutional encoder. So, this was my decoder 1, if I want to call it, and this was my decoder 2. So, what are the inputs to decoder 1? Now, decoder 1, I should be sending in the received information bits and the received parity bits. So, that is what I am sending here. You see here I have written xn is actually my received information bit, and y1n is my received parity bit corresponding to the encoder 1. So, these are the two input to the decoder 1. Now, what are the inputs to decoder 2? Now decoder 2 is an interleaved version of information that is been coming to encoder 1. Now here I am receiving information bit directly. So the received information bit that I will feed to the decoder 2, because this information bit is getting interleaved before being sent to encoder 1. What I am going to do is, so this is my received information sequence. So what I do is, to the second decoder, before I feed this information sequence, I am going to interleave this, so that the order of information bits that is coming here and what is being fed to decoder 2 is same. So we do not send the interleave information sequence in turbo code. From this received sequence, by interleaving, I can get back the information sequence that is being fed to this decoder. So the information sequence input to this decoder is nothing but the interleaved version of the received information sequence. Now what is the second input to this decoder? This received parity bit, and that I am denoting by Y2N. Fine. So these are the two inputs which I am receiving from the channel, which I am feeding to decoder. So the input to decoder 1 are these two inputs, and input to the decoder 2 is interleaved version of the information sequence and this particular parity bit. So these are the two inputs to the decoders from the channel. What else is input to this decoder? There is a third input to this decoder, which is this one and this one. And what is this input? This is a priori knowledge about the information sequence. What is the a priori knowledge about this information sequence that is being fed here as third input? So this third input that you see to decoder 1 is the a priori knowledge about the information sequence. Now how do we get this a priori knowledge? Now initially when we start decoding, we do not have any a priori knowledge about the information bit. So we would assume that the information bit is equally likely to be 0 or 1. So the likelihood of the information being 0 or 1, that is 1. Basically it is equally likely whether the bit is 0 or 1. So that would be our initial a priori information. Now once we feed these three inputs to this decoder 1, now let us pay attention to the outputs of decoder 1. So decoder 1 is giving us two information, one what we call extrinsic information. Now this is information which this decoder computes based on the trellis structure of this convolutional code, and this extrinsic information is being passed to the decoder 1, and this input is fed as a priori knowledge to the second decoder. So you can think of it like this. So there are two decoders who are working independently, but then one decoder, once it decodes information sequence, it passes some information to the other decoder saying, hey, I think the information bit is likely to be 0 with this probability and information bit is 1 with this probability. So the other decoder will take that as an input and then recomputes its probability, and then it will again compute some new probabilities of bit being 0 and 1, and it will pass that information back to the first decoder saying, no, I think it is likely to be 0 with this probability and likely to be 1 with this probability. And this information exchange happens in a regular fashion in this until they converge to a particular decision. We may stop iteration after fixed number of iteration, or we could use some sort of a stopping criteria to do that. So the third input is the a priori input. The other two inputs are the input received from the channel. Now, what this decoder 1 does, it tries to find some estimate about the information sequence, pass it on to the second decoder. Now, this input is fed as a priori input. Now, what is the use of this interleaver? Now, note that the order of information bit here and the order of information bit here. Now, the information bit that is being fed to second encoder, which is this, is interleaved version of the information bit that goes to encoder 1. So, the estimates that encoder 1 gives about the information bits, that has been interleaved and sent to decoder 1. This is to maintain the same order of information sequence as being received by decoder 2. So, because the information sequence here is interleaved version of information sequence here, so we are going to use this interleaver. Now, similarly, this decoder 2, what does this decoder 2 does? It takes these two channel values and it takes this a priori information which it has received from decoder 1, and then it will try to decode this code, and it will form some estimate, some experiencing information, and that information is fed back to first decoder. And note, there is a de-interleaver in between, because the order of information sequence here is de-interleaved version of information that has been fed to encoder 2. So, this de-interleaver is done so that the order of information estimates that we are feeding to encoder 1 is in same order as these other inputs are. So, this is an iterative process which goes on, and after some fixed number of iteration, or you can do some stopping criteria, you can use some stopping criteria. After that, finally you take some decision. So, I can take decision, let us say, from the second decoder. So, this is my a posteriori probability. Now, this information, remember the information sequence ordering at encoder 2 is interleaved version of the information sequence of encoder 1. So, if you want to know the order of information sequence here, we need to de-interleaved this data, and here then we will take a hard decision and take a decision whether the bits are 0 or 1. So, you can see this is an iterative decoding algorithm, where instead of decoding this whole code at one go, what we are trying to do is we are trying to decode first encoder 1, and then encoder 1 is passing some information to encoder 2. Encoder 2 receives some information from the channel and it receives some information from encoder 1. Using this, it tries to form some opinion about the information bits, which is passes it on to decoder 1, and then decoder 1 uses that information. So, one iteration is when this decoder 1 has finished decoding and decoder 2 has also finished decoding. So, that is my one full iteration. Now, what is the algorithm which is used inside of this? I said soft input and soft output decoder. I said input is soft, output is soft, but what sort of algorithms we can use? Now, we can use any algorithm which can take soft inputs and which can give soft outputs, and one of the most commonly used algorithm is our BCJR algorithm. Now, in lecture 5 we have talked about decoding of BCJR algorithm for convolutional code. So, this is precisely what these two decoders that you see here, they are going to use. They are going to use BCJR algorithm, and we are going to slightly modify this algorithm to get these extrinsic informations from the decoder, and that will show in subsequent slide. So, this is the basic block diagram of your turbo decoder. You have to remember this, and again I repeat, each of these decoders are independently working in the sense there is channel input which has been fed back, and there is some a priori information which is coming from the other decoder which is being fed to these decoder, and these decoders take these 3 inputs and they compute 2 values. One is this a posteriori probability, another is extrinsic information. Extrinsic information is passed on to the other decoder as a priori value, and the a posteriori probability is used when we want to take the final decision about the bits. So, let us just review BCGR algorithm very quickly. Now, we have already derived the expressions for the channel matrix, the matrix that we need to compute in BCGR algorithm. So, we are just going to directly write the expression for BCGR algorithm. Now, I just want to introduce an operator which I call max star operator. Now, what is a max star operator? Max star operator of x and y, it's basically defined as log of e to power x plus e to power y. Now, this log of e to power x plus e to power y, this can be written as log of, let us say, e to power x into 1 plus e so y minus x. We can write it this way, correct? Now, this can be written as log of e to power x plus log of 1 minus 1 plus e to power y minus x. Or I can also write the same thing as log of e to power y 1 plus e to power x minus y log of e to power y plus log of 1 plus e to power x minus y. And what is this log of e to power x? That is just x. So, this can be written as this can be just written as x plus this and y plus this. Or I can write this max star x y as maximum of x and y plus natural log of 1 plus e raised to power minus absolute value of x minus y, right. So, whenever I have to take log of terms of this form, I can actually implement it simply like maximum of these 2 operator x and y plus some correction term which can be implemented with a table lookup kind of thing. And this operator can be extended for more than 2 operations. So, if you want to find max star of x, y and z, then I can write it as natural log of ex plus ey plus z, and I can do max star of x, y and z, and then I take the max star of x, y and z. So, I can iteratively apply this max star operator to compute quantities of this form, okay, which is log of summation terms. Now, where do we encounter log of summation terms? I will come to that. Now, this branch metric, this we have derived in one of the lectures, is given by this expression. This is a priori information, this information bit, this is depends on channel SNR, this is receive sequence, transmitted code, receive sequence, transmitted code word. So, this you already are familiar with because we have derived this expression before. Now, recall there were 3 quantities that we need to evaluate when we want to apply BCGR algorithm. And what are those 3 quantities? One was this alphas, which was the forward recursion. Second was this betas, which was the backward recursion. And then we had this channel matrix, branch matrix, right, gammas. Now, if you recall what was alphas, so if you just draw a simple trellis diagram, let us just draw a simple trellis diagram, a two state trellis, and this is alpha at time, let's say L minus 1, this is alpha at time L. Let's just call it a state 0, let's call it state 1. Then what is, let's say I want to compute alpha at time L for state 0. What is it equal to? Recall this was equal to, so there are two states, there are two branches which are terminating here, one is this one, other is this one. So then alpha 0 will be alpha L minus 1 0 times branch metric corresponding to this, which will be gamma 0 0 plus alpha L minus 1 1 times this branch metric, which is gamma 1 0. So if you recall, we had terms of the form summation alpha L minus 1 times some gamma. So those were our terms. Now if we take log of that, so these were our alphas, we are defining a new operator alpha star. So that's a log of these alphas. So what's going to happen here? So you have log of summation terms, right? So if you can think of it as, so here you have terms of the form like this, a1 b1 plus a2 b2, and we are taking log of this. Now we can also write this in terms of, let's say, e raised to power a1 dash e raised to power b1 dash plus e raised to power a2 dash e raised to power b2 dash, right? So if we take log of this, then this will become, because this is like e of ex plus 1 plus, so this, when we take log of these summation terms, we get this max star operator. So we will get this max star operator, and this product term, when we take log, they will become summation. So this forward metric will become, when we implement it in, we take log of this will become a max star operator, and these two terms inside, which is this gamma term and this alpha terms, this will be plus. So the forward metric here in log domain will be given by this metric. Max star operator, we are summing over all the branches that are terminating at this state, and this will be gamma plus alpha star. So this will be the forward metric in the log domain. Now recall, how did we initialize the alphas when we were working in probability domain? We said that the encoder starts from all 0 state. So at time 0 it will be at all 0 states. The probability of its being in all 0 state at time 0 is 1, for all other it's 0. So when we take log of that, then the initialization will become for state, initial state 0, then this will become log of 1 will become 0, and for all probability of its being all other state, this will then become minus infinity. Okay. So if we are writing our recursion in this fashion using max star operation, then the initialization should be done like this. When it's in state 0, the initialization alpha 0 star 0 will be 0, and it will be minus infinity for all other cases. Now if you are wondering why am I switching from probability domain to this log domain, you can see that we have shown this max star operator can be very easily implemented, because this is just maximum of xy plus some correction term. So this can be easily implemented, and that's why we are rewriting our forward recursion, backward recursion, gamma in terms of log domain, so that in our expression where we had this summation, now that has been replaced by max star operator. Wherever we had multiplication, that has been now replaced by addition. So, following the same logic, we can write the backward matrix in log domain in this particular fashion. So, this max star operator, and this is sum of this branch matrix in the log domain and the betas in the log domain. And again, if you can recall, how were we computing betas? So, let us say you had some this thing. So, if you are interested in computing beta for beta at L 0, you will be beta, and this is, let us say this is time L plus 1, beta at time L, this is beta at time L plus 1, beta L 0 will be. So, these are the two branches that are terminating here. So, beta L plus 1 0 times branch metric of this, which is gamma L 0 0 plus beta L plus 1, this is state 0, this is state 1, beta L 1 times gamma L 0 1. This we have already studied when we did BCGR algorithm. We are just rewriting the expression in terms of log, so that our addition term here becomes max star operator, and the product term here that you see becomes addition term. And similar to alpha bit initialization, if we are terminating our convolutional encoder, then beta k at s equal to 0 will be 0, and for all other state it will be minus infinity. And of course, if we are not terminating it, then its probability of being any state is basically same. And if you recall our APP log likelihood value, this was again summation of product of 3 terms, alpha at time L, beta at time L plus 1 and gamma. So, that, and there were 2 terms, one term in the numerator corresponding to all those transitions belonging to information bit being plus 1, and in the denominator we had some terms related to transitions that belong to information bit being minus 1. So, this term that you see here is the term corresponding to the numerator term. Again, the summation term has been replaced by this max star operator, and this product term has been replaced by these addition terms. Okay. And similarly, this corresponds to all those transitions where my information bit is plus 1, and in the denominator we had this. So, we take log of them, so become minus of this, and the denominator corresponds to all those transitions which belong to information bit being minus 1. And again, the addition term that we had in the probability domain description of BCGR, that is now max star operator, and the product terms that we had in the BCGR algorithm are now addition term. So, this is rewriting the expressions for forward recursion, backward recursion, and log likelihood ratio a posteriori probability L value computation for the BCGR algorithm. So, again we will go back to this decoder diagram that we have shown you before. I am reproducing the decoder for rate 1/3 turbo code. This is my decoder 1 corresponding to encoder 1, this is my decoder 2. These 2 inputs that you see are my inputs corresponding to the received information bit and the corresponding parity bit. This is my received information bit, which is interleaved before being sent to decoder 2, and this is the this is a bit corresponding to the received second parity bit. I also said there is a third input, which is the a priori value. Note this a priori value is coming from the other decoder, and since the order of information bit here is de-interleaved version of the order of information bit at second decoder. So, you de-interleave it and send this information here, and the a priori value that you send here is coming from this decoder, and I am interleaving this because the order of information bit at decoder 2 is interleaved version of the order of information bit at decoder 1. This one more thing I am computing here, and I have talked about extrinsic value, right. So, what is my extrinsic value? So, this is what I am computing here. So, let us pay some attention to this is the extrinsic value. So, what is this extrinsic value? So, note I am getting this APPL value computed, that is this. From there I am subtracting the contribution of the information bit. This term is same as this bit. This LC term depends on received SNR. I will come to that. This term is this, and this is the received value corresponding to the information bit, and this is the term corresponding to APPL value. So, what I am doing is I am subtracting from the APPL value the contribution of this received bit. I am also subtracting from this contribution this a priori information. So, what I get is my extrinsic information. So, it's like you can think of it as some additional information about the information bits that has been derived from the structure of the convolutional encoder. And how am I computing this extrinsic information? From the APPL value, I am subtracting the contribution of the received channel bit, I am subtracting the contribution of the a priori value. What is left is extrinsic information, and this information, as I said, is being passed, is interleaved because the order of the information bit in the second decoder is interleaved version of the order of bits in decoder 1. So, I interleave it and feed this as a priori information. So, this is my a priori information. So, this is how I compute the extrinsic information for decoder 1. Now, how do I compute extrinsic information for decoder 2? The same procedure. This is my APPL value correspond to the information bit. I subtract from there the contribution of information bit. This is my LC RL R0 term, and then I am subtracting this contribution of the a priori information. So, what is left is this information, which is my extrinsic information. So, for the second decoder, in the similar fashion, I compute the extrinsic information. I subtract from the APP value the contribution of the information bit and contribution of the a priori knowledge. What is left with is my extrinsic information. Now, I need to de-interleave this information before feeding it back as a priori information. So, this is my a priori value for decoder 1, and I need to de-interleave it because the order of information bit for decoder 1 is de-interleaved version of the order of information for decoder 2. So, this is how my iterative decoding algorithm is working. Again, I will do a quick recap. So, using the BCGR algorithm, so I have some receipt value from the channel, which is this and this. Initially, I do not have any a priori knowledge about the information bits, so I assume they are equally likely to be 1 or 0. This decoder 1 will apply BCGR algorithm and it will compute the APP L values and it will compute the extrinsic L values. Now, this extrinsic information is passed as a priori information to decoder 2. In addition, decoder 2 has this received parity bit, which is this one, and interleaved version of the information sequence as input. So, it will again compute APP L value and it will subtract the contribution of the information bit and the a priori value, and then we will get back extrinsic information. So, you can see this extrinsic information is getting passed from one decoder to another. Okay. And ideally what we would like is this extrinsic information should grow in a manner so that it push the decision in favor of either information bit being +1 or -1. That is when we say the decoder is converging with iteration. So, we have already explained that there are two decoders and each of them are using map algorithm, this BCGR algorithm that we talked about. There are 3 inputs received from the channel. One corresponds, this RL0 corresponds to the information bit, RL1 corresponds to the parity bit corresponding to encoder 1, and RL2 the parity bit corresponding to encoder 2. So, at each time instance, so this is my time index, time 0, time 1, time k minus 1. So, each time instance I am getting this 3 bit information, which is information bit, first parity bit and the second parity bit. Remember, this is a rate 1/3 code. So, if you have a information block of k, you will get 3k coded bits. 0 is mapped to, in this case, -1, plus 1 is 1. Now, let us compute the log likelihood ratio. So, probability of UL given RL is 0 is given by, what is the probability that UL is +1 given this received sequence RL divided by probability of UL being -1 given received sequence RL. This we can write as probability of R given U multiplied by probability of U, and so that is how we have written it. Now, we can separate out this into 2 terms. So, this is one term we have and this is another term we have. So, log of A times B, log of A plus log of B. So, we can write it as this is one term and this is another term. Now, we are talking about additive white Gaussian noise channel. So, we can find out what is the likelihood ratio. So, we plug that value in here, and after simplification what we get is a term of the form this. So, there are 2 terms, one is this and another is this. Now, what is this? Is 4 times ES by N naught times RL0. RL0 is my information received information sequence. So, this you can 4 ES by N naught I am writing as L sub C and calling it a channel reliability factor. So, it depends on the signal to noise ratio of the channel, and this you can see log of probability of UL being +1 divided by UL being -1. This is a priori knowledge about the information bit being +1 or -1. So, there are 2 inputs, one coming from the channel which is multiplied by this factor LC, and other is a priori knowledge, and that is why you noticed here in the diagram where I had LC times RL0, LC times RL1. This was this channel here at LC times RL0, LC times RL. So, these values, received values were scaled by this channel reliability factor, as you have just derived here. Now, in case of transmitted parity bit, we do not have any a priori knowledge. So, in those case, this will be just LCRL 1 or 2, depending on whether we are considering parity bit 1 or parity bit 2. As I said, initially we do not have any a priori knowledge about whether the bit is plus 1 or minus 1. So, we would assume that it is equally likely to be plus 1 and minus 1. So, the a priori log likelihood value L value will be considered as 0 for the first decoder. But thereafter, this a priori values will be replaced by the extrinsic values received from the other decoder, right. And again, the received values that we got from the channel LC, RL0 and RL1 and RL2, remember to feed them in proper order when you are feeding to decoder 1 and decoder 2. And this we have explained also earlier. You can see when we feed the extrinsic information from decoder 1 to decoder 2, we are interleaving it. Similarly, the information bit that we are feeding to decoder 2, that is an interleaved version of information coming from decoder 1. Similarly, from decoder 2, if we are feeding something back to decoder 1, we are doing de-interleaver, and when we are taking decision from decoder 2, we are also again doing de-interleaving. So, this interleaving, de-interleaving is done so as the order of the information bit is preserved in the fashion they are entering encoder 1 and encoder 2. So, as I said, there are 3 inputs to this decoder, this channel receipt value corresponding to information sequence and parity bit and a priori value, and there are 2 output. One is this APPL value that we have computed, and the second is extrinsic value. And how are we computing extrinsic value? From the APPL value, we are subtracting the contribution of the received channel value, and we are subtracting the contribution of a priori value, which is nothing but extrinsic value of the other decoder. Okay. So, this we have explained. So, this is the APPL value and this is the extrinsic L value. So, why are we subtracting these terms, this information bit term and the a priori term? So, we essentially are trying to remove the effect of the current bit in some sense from the APP value. So, in some sense we are trying to provide some independent estimate, because this anyway this a priori information has come from the previous extrinsic information from the previous decoder. So, there is no point feeding the same information back to the same decoder, and the receipt values are already received by the decoder. So, we are trying to in one way trying to send some independent estimate about what we think the bits are to the other decoder, and that is the whole idea behind this iterative process, that you want to give some sort of independent estimate. If you try to feed the same information back, then it will become a positive feedback system and unstable, the decoder may not converge. So, that we do not want. And in the same fashion, the decoder 2 will also have 2 terms. One is this APP value and other is this extrinsic values. I have already explained what are the inputs to the decoder. I will again repeat: one term corresponding to the received information bit, one term corresponding to the received parity bit, and one term corresponding to the a priori information which is being fed from the second decoder. You can see basically a priori information for decoder 1 is nothing but extrinsic information coming from decoder 2 after proper interleaving, de-interleaving, because you want to ensure that the order of the information bit is same. Okay, this I have explained in the initial iteration. Extrinsic information is basically 0 and subsequently a priori information is 0 and subsequently the a priori value will be nothing but the extrinsic information. So, this process, as I said, goes on repeatedly iterative fashion. So, let us take an example and see how this works. So, we are considering a rate 1/3 turbo code where the constituent encoder is this 2-state encoder. So, our turbo code is this. Each one of them is using this 2-state recursive convolution encoder. This is my interleaver and this is the state diagram corresponding to these convolutional encoder. Okay. Consider an information bit length of 4 and let us say I am doing block interleaving. So, I am feeding the data block wise and reading it column wise. So, as I said, I am mapping 0 to -1 here and 1 to +1. So, if this is my input block, the interleaved block is given by u hat and corresponding parity for the first encoder is given by this and the parity due to second encoder is given by this. So, I use notation P1 to denote the parity coming from the first encoder, P2 to denote the parity coming from the second encoder. U is my information sequence, U hat is the interleaved version of information sequence which has been fed to encoder 2. So, I will just show you basically, I will just, and I am assuming a channel 1/4. So, the likelihood channel like reliability factor LC will be basically 1. So, LCRI will be in my case would be same as the received value for this particular signal to noise ratio. This is just a toy example to illustrate how this decoding works. So, these are my information bits U0, U1, U2, U3. So, as I said, if it is a 0 I am mapping it to -1, if it is a plus I am mapping to +1. So, the information sequence here U0 is 0, U1 is 1, U2 is 0 and U3 is 1. These are the corresponding parities for this information sequence from the encoder 1 and these are the corresponding parities from the encoder 2. Now, what I have here is the received values. So, you can see here, so this was transmitted as plus, I received a plus, this is transmitted plus, I received a plus, this was transmitted -1, this was a minus, but here the sign has changed. Note here, this was transmitted as -1, but what I received is plus 0.8. So, this bit is received in error. Now, let us see using this turbo decoding how we are able to correct this error. So, of course, the first half of decoding will be I will decode, I will have decoder 1 work first and then decoder 2. So, I will just directly come to the values because I have already explained the whole procedure. I will just show you the extrinsic information value and the APP values at the end of each iteration. So, this is the extrinsic information after I have decoded using decoder 1. This is the extrinsic information after decoder 2, and this is the APP value after decoder 1. Note that I have transmitted 0, 1, 0, 1. So, there the sign is okay, there the sign is not okay. This is after first decoding, this is in error, this sign is okay, this sign is okay. Now, next, so this whole thing was my first iteration. This is my first iteration. Fine. Now, what about second iteration? So again I first compute the extrinsic values. This is after I do decoder 1. This is extrinsic information after I have done decoder 2, and this is the APP value, L value, APP L value after decoder 2, and note here this was 0, this is 1, this is 0, this is 1. So, after 2 iteration I am able to correct the transmission error. So, with this I am going to conclude our discussion on turbo decoding. Thank you.